Hello everyone, my name is Aditi Dhamankar and I am a student of Ramdev Baba University. The topic that I am going to explain today is Deutsch algorithm. But before looking at Deutsch algorithm, let us first uh, have a look on quantum oracles. As we are going to use quantum oracles in Deutsch algorithm, it is important to know about them. Quantum oracle is a black box which is used extensively in quantum algorithms for the estimation of function using qubits. Now let us see at the circuit diagram of quantum oracle. Quantum oracle has two inputs, gate X and gate Y. These are connected to a black box. We can call it as a U of F, and it has two outputs, that is gate X, which is the output of gate X, and gate Y XOR f of X, which is the output of the second qubit, that is gate Y. The oracle acts on the state X and Y and turns into X and Y XOR f of X. We can also write this as a gate X, gate Y. When it is operated in oracle in the black box, we get gate of X and Y XOR f of X. Here the gate Y bit is converted into a function, that is the f of X. Now if we put y is equals to 0 in the above equation, we can write it as gate X, gate 0 when it is operated in the oracle gives gate X and 0 XOR f of X, gate of f of X, which further gives as a gate X, gate 0 gives gate X and gate f of X. Basically, the oracle is used for the estimation of function using qubits. This is the only concept that we need to know. The important thing here is that the gate Y is converted into gate Y XOR f of X. Now let us look at the Deutsch algorithm. Deutsch algorithm is an example of a quantum algorithm that can solve a problem faster than any classical algorithm. Faster in this context means that the algorithm is solved in a very specific problem and is solved in a one go. Definition of Deutsch algorithm is given as f of 0, 1 gives 0, 1. Here the function f takes a single bit as input and yields a single bit as output. Either it can take 0 or 1 and yield 0 or 1. Here basically our goal is to determine whether the function f is constant or balanced. Constant, let us see what is mean by constant in this algorithm. A function is called constant if it produces the same output regardless of the input it receives. Let us say f of x is equal to f of y for all x comma y. That is, let us see this with the help of a truth table. Let us put the value of x as 0 and 1 and f of x as 0, 0. Here we can see that the input that we have given is 0 and 1. Regardless of the input, the output is always 0. This case is called as constant. Let us assume this as case 1. Now in case 2, we will put x as 0, 1, the same as before, and the f of x will be changed to 0. Sorry, f of x will change to 1, 1 and will change to 1. Here, the input is 0, 1 and the output is 1 regardless of the input. This state is called as constant. Now, let us take a look at balanced. A function is called as balanced if it yields 0 for half of a possible input and 1 for the other half. That is, for half of the input, it yields 0, that is, f of x is equal to 0. And for the other half, it yields 1, that is f of x is equal to 1, sorry. Let us assume this case of constant as case 2. Let us understand the balance case with truth table. Here we will give the input as 0, 1 and we will get the output as 0 and 1. And let us consider this as case 3. And in case 4, we will give the input as 0, 1 and we will get the output as 1, 0. Here the output is not constant as it was in the constant state. If in constant state we give 0 and 1 as the input, but we received only 1 as the output, either 0 or 1. Here in balanced state, we are giving the input as 0 and 1 and we are getting the output as 0 or 1. Either the 0 is on the upper side or on the lower side. Let us consider this case as 4. Now, to solve the dash problem, we have to call the function f of x twice in a classical computer. If both the output are same, then it is considered as constant, otherwise it is considered as balanced. But in quantum, we have to call the function f of x only once, as it employs the superposition of all the inputs. This superposition results in increased speed of the algorithm. Now let us take a look at the circuit of the Deutsch algorithm. This takes two input as gate 0 and gate 1, and these inputs are processed by Hadamard gates. And the results of these are passed to the U of f. That is the oracle that we have seen in the quantum oracle. As we have seen earlier that U of f gate takes input as gate x and gate y and gives the output as gate x and gate of y XOR f of x. The Hadamard gate is once again applied to the first input, that is gate 0, and the qubit 1 is measured. Now let us claim that if we measure 0 on the first qubit, that is gate 0, then the function must be constant or it is balanced. To verify our assumption, we will divide the circuit in 4 different stages. The first stage is called as gate psi 1. The second stage is called as gate psi 2. The third stage is called as gate psi 3, and the fourth stage is called as gate psi 4. Gate psi 1 is equal to gate 0 tensor product of gate 1. The gate psi 2 is given as here the Hadamard gate is applied to both the qubits, that is the gate 0 and gate 1, which is equal to 1 by root 2 gate 0 plus gate 1 into 1 by root 2 gate 0 minus gate 1. Taking 1 by root 2 common, we get gate 0 plus gate 1 into gate 0 minus gate 1. Multiplying them, we get 1 by root 2 gate 0 0 minus gate 0 1 plus gate 1 0 minus gate 1 1. Now to calculate gate of psi 3, we will apply the UF gate to gate psi 2, that is UF into gate of psi 2, which is basically equal to 1 by root 2 into gate 0 gate 0 gate of f of 0 XOR 0 minus gate 0 f of 0 XOR 1 plus gate 1 gate 1 gate of f of 1 XOR 0 minus f of gate of 1 gate of f of 1 XOR 1. Now let us recall our case 1 that we discussed during the definition, that is f of 1 is equal to f of 0 is equal to 0. Therefore, it simplifies gate of psi 3 as, which is equal to 1 by root 2. We will put 0 in place of f of 0 and f of 1. that is kth 0, kth of 0 XOR 0 minus kth 0, kth of 0 XOR 1 plus kth 1, kth of 0 XOR 0 minus kth 1, kth of 0 XOR 1. Now, as we know that 0 XOR 0, as we all know, 0 XOR 0 is equal to 0 and 0 XOR 1 is equal to 1. Therefore, the equation becomes 1 by root 2 kth 0 kth 0 minus kth 0 kth 1 plus kth 1 kth 0 minus kth 1 kth 1. Taking kth 0 and kth 1 common, we get kth 0 in bracket kth 0 minus kth 1 plus kth 1 in bracket kth 0 minus kth 1, which is equal to 1 by root, which is equal to 1 by root 2 kth 0 plus kth 1 into kth 0 minus kth 1. To calculate kth of psi 4, kth psi 4, we need to apply Hadamard gate to the first qubit. That is kth 0 plus kth 1 upon under root of 2 into kth 0 minus kth 1 upon under root of 2. Here it is important to note that the first qubit is in kth plus state. Now applying Hadamard gate to the kth plus state, we get kth 0. Therefore, when we measure the first qubit, we will get kth 0 with 100% probability. Here, kth plus is equal to kth 0 plus kth 1 upon root 2 and kth minus is equal to kth 0 minus kth 1 upon root 2. Now let us see the conclusion. When the function is constant in psi 3, in kth psi 3, the first qubit, that is kx, will be either plus minus kth plus, and the second qubit, that is ky, will be kth minus. That is, when we apply Hadamard gate to the first qubit, we get kth 0, which gives us 100% probability of getting kth 0. But when the function is balanced in kth psi 3, the first qubit, this is for constant, and for balanced, in kth psi 3, the first qubit, that is the kx, will be equal to plus minus kth minus and the second qubit, that is kate y, will be equal to kate minus. Therefore, applying Hadamard gate to the first qubit converts it into kate 1. That is which gives us the 100% probability of getting kate 1. Here we have seen that in the Deutsch algorithm, if the function is constant, then we will get kate 0, and if the function is balanced, then we will get kate 1 with 100% probability. This is the Deutsch algorithm. Thank you.